I would like to say thank you so much to Georg. Georg is the sponsor tonight. He is the CEO and owner of Type Stress Inc. Corporation. I met him, I think exactly 1 year ago. Well, yesterday was a year ago when I finally sent him an email to invite him to be part of the association, and he kindly responded my email. We started getting in touch, and I convinced him to come and give a presentation. He came all the way from Santa Barbara, California, and I'm really happy. I met him last night in person. We went out for dinner. I met his wife, his father, who is also a very experienced engineer as well. So I'm really glad to meet you. It's been so nice. I enjoyed the dinner last night. Thank you so much. And well, they are the sponsors tonight. Type Stress Incorporated.
I'm happy to be here. Thanks, Juan, for having me. I had almost as bad an idea. If you can't read these are pictures of what different people perceive engineers to be. Like the train driver. I think we all know that. I know that when I started 35 years ago in my first engineering job, I had a bit of a misconception, let's say, or an inaccurate idea of what my job was going to look like. I don't know that my ideas have gotten better, but two things I know with certainty. An engineer is a person that gets excited about things nobody else cares about. And a person that solves problems that you didn't know you had. So hopefully, you know the problems you have, and maybe I can even point you in the right direction. So, the topics, I have one general topic that I want to speak to you about, and that is calculated results in a search analysis versus actual results, which are pretty much what we observe in the plan. Because we can't, actual results is essentially what we observe in the plan. So, what causes the differences between what we calculate? Why does it matter, and how do we minimize these differences? And I'm going to tell you a little bit also about the Rohr 2 pipe stress program. I was reminded, I have to say, what Rohr even means. Rohr means pipe in German. It's a German product. I've used it for just about 30 years. I've used Caesar for just as long, pretty much, and other auto pipe, pretty much all products. All right, let's dive right in. So you'll see this screen occasionally, and you'll know kind of where we are. So we are at the top. Let's talk about something relatively easy. If we have the dead load that's on an equipment nozzle. So, you can't see, that's the equipment nozzle. Doesn't really matter, but that's the equipment nozzle. We have a spring hanger here, and we have some supports on the pipe. When one puts this kind of geometry in the Caesar or 2, it doesn't matter. The weight will distribute itself statically, and you'll have, let's say, half of this piece of weight on the nozzle, as well as a flange and some things in the local area. There's vendors on equipment, for example, in turbines, that say we don't want to have cold load on the nozzle because we want to see the flange, the piping flange, float above the nozzle, and we want it to be parallel too. We don't want to be top, because now when you tighten the bolts, you're going to get a moment. So what do we do? Well, then they don't want to load either. So we start pulling on this spring, and you use free code, free node, whatever. In Caesar, if you know what I'm talking about, raise your hand. All right, you guys are awake. Good. Oh, Richard, you know this? And so the effort is, and you have a very similar function in Rohr 2. The effort is, I'm going to start pulling the load off of the nozzle. The problem is that as you pull here, you get a moment here that was previously not there. There might have been a little moment due to the deflection of the pipe, but as you start pulling, the little moment goes away to zero, and it gets larger and larger because the pipe, you're basically pulling the pipe up and you're getting a bow in the pipe, and now because this is attached to the turbine, you get a moment. And then you say, well, I don't want this moment. And we need a free moment, not just a free load. Okay, so what do we do? I'm going to show you, but I'm going to let you hang on that for a moment. But that's the divergence, because if they actually would make the last weld just a little bit, let's call it a miter, but it's not a miter, maybe it's a half a tenth of a degree, but they make the last weld so that it's flush, then we're modeling a moment or a load that's not really there. Alright, so let's talk about divergence in operating load cases. Here's a job I did just 2 months ago. These kind of things are something you're very familiar with, especially east of Houston. My client said, here's what we're going to do. We're going to hold on to the pipe here in all translational directions. We're going to guide it a couple places down the tower. Very common arrangement that you hold the weight of the pipe near the nozzle at the top, right? So you have very minimal strain in the thermal cases between the support and the nozzle. So if you put this into Caesar or Roar 2, what happens is the weight of the pipe, this is a 4-inch pipe, it's not a huge pipe, but the weight is going to distribute itself not only to there, there's going to be weight on the nozzle too. So you're going to have weight at the nozzle, you're going to have weight there. It's going to distribute itself based on the relative stiffnesses of these different things. Plus there's a ton of weight in this case up here near the nozzle, so a lot of that's going to go on the nozzle anyway. So my client says, I had about 400 pounds up here and 500 pounds here. Just a relation that's not a very heavy pipe. And they said, no, we want the 900 pounds down here and we want 0 up here. What's an engineer to do? Well, that's not the way the program works, right? You put it in, I have a hard time connecting it and not connecting it, right? So there's no free node, there's no string. And my client says, well, tough. I want to see the 900, I want to see 0. We are going to build this, we're going to hang the thing there, and we're going to put a rig in, right? And we're going to rig the pipe, and we're going to make that last weld. And we're going to have 0, because this client has had nozzle cracks, and is very sensitive. They don't want to have those nozzle cracks. Now, so I'm going to come back to that. I'm going to show you what I do and what I did for this client. We're going to talk a little bit more about engineering and general things. So, another thing is that in this case, let me show you this. You could have in the operating case divergences based on, because it's very much based on these relative stiffnesses. We're fairly confident about the stiffness of a pipe, but we're very not maybe as confident about this plate that's holding it, especially where the plate hits the vessel, right? There's spring stiffnesses. It gets pretty muddy there, and if it's too muddy, we're having divergence. When I say the word divergence, I want you to think about calculation reality. That's the divergence I keep referring to. And since a lot of this talks about that divergence and what we do about it and where they happen, you're going to hear that word a lot. So one of the things one can do is to get a realistic nozzle stiffness or stiffness. In this case, I did model this plate and this portion of the vessel in FEA. In another job, the gray is the beam theory model, and then the beam theory is basically a line of stiffness. Then you get a spoke out to a plates and shells model in the FEA model, and then you go back to beam theory, and so forth. You go in work 2, you can actually have the beam model and the plates and shells model in the same calculation kernel. So the stiffnesses are, or the loads and the stiffnesses are iterating together. Way back in the day, I bought FE pipe from Tony Poland. This was the beginning of the 90s. And we take loads, I take loads out of Caesar, put them in FE pipe, and in Caesar I'd have to assume an infinite stiffness, or something, and then I go to FE pipe, and then I put that load that comes out of Caesar in FE pipe, I get deformation, I go back and put that deformation in Caesar, and then they go, well, that deformation, the load's lower. So then I go back over here and I put a lower load, then the deformation's lower, and you go back and forth, and you actually do converge on a solution. It doesn't take forever, but it's kind of a pain. Here it's all in this package. It's one of the things I really like about it.
All
right, go.
What type of element do you have going to the mesh for this nozzle?
What kind of element?
Yeah, what type of element do you have going to the meshing for this nozzle?
Rick,
Is it just a shell or is it a solid?
Shell, and it's not solid. It's a 2D element.
No.
So
When you do the mashing for the nozzle area,
Yeah.
you have to specify the type of element.
Yeah, it's a 2D plate with thickness. It's not.
But it's not a 3D element.
And
So
that's right.
it's not a 3D element?
It's not a 3D element. This is 1D element. Pipe stress model is 1D element. Then you have a 2D element. But I can talk to you about it specifically afterwards. Let me move along and
Okay.
anyway, anybody who wants to communicate me, take my card, have a WebEx. I'm very happy to share. Let me just tell you, because as a person, every person kind of comes from a perspective. I'm going to spend a lot of time on what I've done with my life, but I will just highlight a few things. So, I started in Philadelphia Electric and piping in-service inspection. After grad school and after some other jobs and things, I've worked with my dad, who's here, turbo machinery expert for a long, long time. Built the ethylene plants, or what are they? The East Massachusetts big. Channelview, the olefin plants that are there in the 1970, 2 or 3, 4, something like that. Turbo machinery guy. Anyway, so at the time in the early 90s, he had a lot of clients that had turbine problems that were piping related. That kind of drew me into piping. I came to Houston, took some piping courses. I worked for an engineering company in Germany. That's how I found out about Roar 2. Otherwise, I probably would have never heard about it. Like many of you, probably never heard about it. I got involved in a lot of Siemens power plant design. Then I sold engineering out of Naumann, Denver. And we did design stress analysis, support design, kind of the whole piping design package in Caesar and other programs. Pretty much been in every industry. Just in the last year, pulp, steel mill, Canada, oil and gas. Since that's kind of booming, I get some more from those guys too. So, all right. Now next topic about divergence, and that is frictional resistances that cause divergence. This whole thing about frictional resistances is a big topic and problem with pipe stress, because the frictional resistance is essentially a force that is opposing the movement that the program calculates. And all these forces oppose the movement by the friction coefficient times how much weight's there. So there's kind of a lot of different things that the friction causes divergence. And one way, I'm going to move at some point into how do we solve this, because one way that we do solve that is to try to bracket the problem, because it can get friction can be kind of a very large problem. So I've drawn the same system, and if you would imagine there would be shoes here. This is one way friction can cause divergence. If this is going this way, and basically this pipe is going like that, I hope you can see me. The friction in this leg would be resisting this elbow going that way, right? And this leg would kind of go like that because the frictional resistance it would be pushing against it and would be not allowing it to move maybe as far, and so this moment would be reduced because of the frictional resistance. So if so the cold to hot would be in that situation. What about when, and friction is of course not a one-time event. So it resists and then it kind of slips, right? Because the kinetic friction, the static friction. Resists, slips. Does this many, many times during the warm-up. But essentially you're only seeing one side of the moment, and because we don't show that it slips, we just see these opposing forces, you can actually have a nozzle load lower than it actually would there be no friction. Well, we can't rely on friction to help us out with our nozzle loads, right? For starters, one can run an operating case without friction. What I would also point out is often, when you pull on this string, okay, often, the moment that you're putting on the nozzle is the opposite of the moment once it gets hot. And I'm not going to ask you to raise your hand, but I've done this, and I'm not proud of myself, where the cold moment, essentially, let's say you're allowed 1,000 foot-pounds. I don't even know what to talk about because you're laughing, I think. But if the moment is 1,000 foot-pounds is allowed, and you put a cold moment of negative 1,000, and then you have a hot moment of positive 1,000, you've just gone from negative 1,000, you've added 2,000. But if the negative 1,000 isn't right, that is, that they hook the flange up straight, you actually do have 2,000. So you kind of cheat your way to be under the allowable to put kind of almost like a cold spring on the nozzle, okay? Again, divergence, because this is not how it is, it's definitely not conservative. All right, so going back to the friction here, what I would recommend for starters is to have a load case without friction. So let me show you this example. And some of you might not be able to see everything, but I'm going to explain to you. So here's the operating load case, and I can make a new load case. I'm just going to show you this in Word 2, and we'll call it Operation No Friction, or just NF for speed's sake. Okay? And in this friction factor tab, in that load case, I can set a multiplier from 1 to 0, or to whatever I want, for all these different frictional directions, and then I say okay, and I could run the model, and now I would have a dead load case, an operating case, and a no friction case. Okay. Now I can at least see that effect, and if my load on the nozzle went up, it'll actually go up even more when I cool the turbine down, or when I cool the pipe down, right? Because the moment it's going to reverse. I don't want to go too fast, but so slow me down. Yeah, if just tell me. See, this is the thing about me getting excited about things nobody else cares about. Bear that in mind. That's what engineers do. I'll say one word about this moment reversal too. Is that if the pipe bends this way when it heats up, and bends a little this way when it cools down because of the friction, this moment is the total moment is larger than if you would just do the cold to hot. Okay? In fact, the EN 1348 in the European Code requires you to do a hot to cold. Okay? Requires it. So you get the full moment reversal for your stress rating. And I think, as just common sense would tell us, it's a good idea for the nozzle loads, because it's an actual thing that's going to happen when the pipe cools off, right? It's going to pull back. All right. You can interrupt me if you have a quick question. I don't want to take a lot of time going down a bunny trail, because I do, want to finish. Okay, on the same topic of friction, my observations in the plant have many times I've seen this happen. Ratcheting of the pipe. That is, that the friction going one way is a little different than the friction coming back. So it doesn't end up where it started out. Again, divergence. Because in our models, we go cold to hot, boom, here's the loads, end of story. However, in real life, pipes tend to ratchet themselves to places you could have never imagined till they're off the steel. They were once in there, now they're down there, and this poor guy that used to have his help is now bent, right? This happens fairly often. And so, let me show you what I do for that ratcheting kind of thing. So I've made a model that's very simple, and so not only can I in Word 2 go cold to hot, I can go from hot to cold. And then I can tell Word 2 in one load case called a follow-up load case, repeat this 1,000 times. Okay? Usually if you repeat it 40 times or something, you're going to see if something's happening. If it's just like, or if it's actually going somewhere. So I've done that. I have load case successions of 4 different load cases, and I run those 60 times. So there's actually 240 successions. So when I do that in this case, and look at the result, and this is called the follow-up load case. These are all the load cases. I'm not gonna run it or show you, because half you probably can't see it anyway. But I'm gonna show you just an overview. This is where it ends up. This pipe has a tendency to ratchet itself over here like that. Okay? Now you can say, well, then you guide it. Yeah. We're going to get there. I'm not saying you shouldn't guide it, but the ratcheting effect, even when you guide it, I'll show you some photos from plants where this has happened besides ones I just showed you. All right, so if I go to a node here for example, and I say, show me these results, all these load cases, and show me a diagram. All right, so what you can see from this diagram is that node that I just clicked on, blue is Z, which is, in this case, vertical. Doesn't really go anywhere. That elbow bounces up and down just a little bit as it gets warm and cold. Because it's all kind of, supported at that elevation. X goes a little bit to the side, but kind of stays there too as it warms up, cool down. But Y just goes somewhere until it ends up leveling out. The Y ratchets itself. So these load cases just keep repeating until at about 100 load cases under 20 inches. Extreme example, but it's to make the point. We have to be careful about this ratcheting, and this idea from hot to cold, or even repeating the cold to hot and hot to cold, is a good thing to in some cases to look at and to consider. All right, let me close this real quick, and can't see my mouse. No, go back to my presentation. So, here's a large bore pipe, 20 inches, ratchet itself, not a good situation. This is an interesting case. I'll confess, on a plant I designed in '99. Took this photo, I came back. This is a pipe, a bypass pipe goes into the condenser. This is attached to the condenser in the very near proximity. The spring started out there. It's not. It hasn't fallen off yet, but it's getting mighty close. So every job, luckily, I get to learn too. All right, we talked about how the friction is nonlinear. That is, there's not only the static coefficient, but the kinetic one, and it kind of shifts a bunch. So, and depending on how much stiffness the steel has to give, and then kind of bounce back, you can make a huge steel model. This is in Roar 2 in the steel model. But in the end, if we don't bracket the problem properly, like this broke out from a frictional, the friction was not looked at correctly, and the calculation pulled the Hilties out of the ground. So there's a lot. I can show you. I got mounds of pictures of things that happen in the plants. I'm going to bore you with all of them. All right. The next topic that I want to talk to you about is support design. Now I understand some of you aren't support designers. We're more of a pipe stress organization or association. But the pipe stress people have to have some idea about the support design. They have to know that the support design will, in fact, mechanically carry out what they're assuming in the stress analysis, and often that's not the case due to, workflow and so forth. I'm not going to go through this all, but the support design is where I'm going to focus on just now here for a couple minutes. It's crucial to ensure that the support design carries out the intended function. I'm going to show you some examples where it didn't, and it's not necessarily the stress guy's fault, but the support guy goes, I'll put a shoe with some clips around it or whatever. I'm going to show you what can happen. And then also, that this is also important, that the stress analysis doesn't make unrealistic demands of the support design. I'll show you an example. All right, I'm going to start with a very easy example. I do some auditing work of stress analyses, and I've tried to erase the innocent, the guilty, so hopefully it'll slip up. But here's a steam pipe. A turbine was here. This is the design. And originally the reason I got involved is the turbine had a problem. And this support here was a moment only support. Okay, you can laugh now.
You can make those things.
You can't go to Caesar and put RX, okay, or RY or RZ. It doesn't work. It doesn't exist. You can't restrain a moment without, first of all, it's questionable whether you should be restraining moments at all in piping. But you can't restrain a moment without also having a translational restraint. This guy, you know, not his fault, probably not educated, like, he's not in Houston. Probably had a big moment here, said, what the hell, what am I going to do? Okay, so he restrained the moment there, and then went to the support designer. Well, that doesn't really, the support designer looked at it, I don't know what it is. What ended up here is a shoe. Yeah, and it was like a little bit of blocks of steel, like, you know, that far away. I mean, it wasn't doing anything. Okay, another example of an unrealistic demand on the support, on the structural guy. 24-inch exhaust line. This was an anchor, like ANC anchor, right? So all translations and rotations are anchored. Well, a 24-inch seam line is not impossible to anchor, but very hard to put on an I-beam and say, yeah, I got this, the moments are zero. They're not, they won't be, and they will pass through, and this poor little NEMA 23 turbine is having a hard time. The pipes don't really cry about it. So a lot of times the evidence is in a cracked nozzle, a turbine that doesn't run, when I'm comparing calculated results to actual results, right? Because the pipes, actually this plant, they did have a 20-inch main steam header failure in a branch, and it's a 10-inch branch. Different story, different reason. Okay, so while I'm here, I do want to mention that this is the novel calcs for the NEMA turbine. I'll show you really in the low case editor. There's a thing called nozzle analysis, right? And I can tell row 2 that it's a NEMA turbine. Here's the 2 nodes. I just pick the nodes. And I say, and then if you don't tell row 2 that one of them is exhaust, it's going to say which one's the exhaust. Because it's kind of important, because the moments are summed around the exhaust. So there's 3 limits for this thing. I mean, the API is similar to NEMA, and the different limits on the forces and moments and the combination of forces and moments at the exhaust. So this is coupled, so for every load case, for dead load, operation 1, operation 2, those things are evaluated in this nozzle analysis, and the results are fed in. You don't have to put how far it is from one nozzle to the other. It's already obvious. It's all in the model, right? And the models don't have to be connected mechanically in row 2. I just put this stick in for my own. If I ever wanted to figure out how far was this from this, and why did I do it, here's my pipe center line. It's just for my own reference later.
Have you download straight from the 3D model into the program, or do you have to redraw the whole thing?
That's a great question. I'm not going to answer right now, but I will answer it shortly. It's a great question, because almost all my work comes from people that made a 3D model. And one of the reasons I love Roar 2 is exactly that reason, because I do import everything. I build nothing from scratch. All right. But I'm going to show you that, what was next. So I show you that. Finishing up with this support design. There are different types of supports. Some have friction, some don't have friction. Some have gaps, some don't have gaps. The gap and friction issue is kind of married, because if you have a frictional support, you kind of need a gap. It's hard to not have a gap, it's going to get stuck, right? So I think as pipe stress people and that drive which support is going where, you have to make a distinction between supports that are near sensitive equipment, which is more or less what I've talked about now. If you got a pipe going down straight down the pipe rack, yeah, it's not that critical whether you have gaps and friction. But it can be too, because the friction can gang up on you, if you know what I mean. All the frictional resistances all add up, and all of a sudden you have a 10 kip load. Your civil guy goes, where do you get this 10 kip load from? Yeah, it's all the frictional resistances ganging up. Which is another reason you could run a no frictional load case to see what part of it is bending the pipe and how much of it is just the friction ganging up. And it's not always conservative, right? So you could have the friction canceling itself, but since it's not all concurrently acting as it does in our programs, It could be, you could have a lower load too. Alright, so make a distinction between supports that you care about and some that you just kind of guide it so it doesn't fall off the rack, right? So, and I'll reiterate, the support design in critical supports, near critical equipment, has to be driven by the stress guide. Somehow, or the management has to follow up to make sure that it's being carried out. I'll show you an example. Here's a pipe, another turbine connection, and this axial stop is on the center line of the turbine. Very good idea. I mean, I'm not saying the pipe design is perfect, but it's a good idea. The pipe comes from somewhere, say, all this growth goes that way because we don't want you to turn in our turbine, right? So, nice axial stop goes there. Problem is, in the analysis, the axial stop has no friction and no gaps. In reality, the support designer designed something with friction and gaps. And I got involved because the turbine was wiggling around and not running well. The nozzle valves are up here. You're not going to be able to see all of it. In operation, I've taken the weight out of it. I've subtracted the weight out of the operation. The numbers work great. No friction, no gap. Perfect. Problem is, you add friction, numbers go up. You add gap, goes up. You add friction and gap, keeps going up. And all of a sudden, we got 11,000. We're allowed 1,600 foot-pounds, and we're at 11,000. Go ahead.
Is that how the report comes out of the program?
This is an Excel table where I tried to show, but I have to show you. Yeah, the reports come out of the program very similar, but this is Excel because I'm trying to show. Here's no friction, no gap. Here's just adding friction, and here's adding both. And I did the moment reversal, so this is going one way, this is cooling off. Heating up, cooling off, and now I have a moment range that's 11,000, and it should be 1. And so I tried to explain that.
At least you can read that. The other stuff that you get from other programs, you can't read. It's a bunch of...
Well, sure enough. Alright, so I want to show you just some physical support. So if you go, well, okay, I understand that this support should have no friction, no gaps. Absolutely it shouldn't, because it messes up all your loads that put friction and gaps in. That's why the guy didn't put friction and gaps in, because he probably realized that. But now the support designer has to carry out this function. Here's how you, and I'm not implying with any of my stuff you guys don't know this, okay? So here's supports with friction and gaps, just some schematic. And because I say you have to have one without friction gaps, I'm showing you a photo of one. Here's a support that's an axial stop. It's only restraining the axial translation. There's no rotational stop. This thing is only stopping the pipe in the axis of the pipe. It can go pretty much everywhere and turn around every axis because it's pinned, okay? And these are rigid struts, and it's even pinned with what's called a round lug that's on the pipe. This is Lasiga hardware. We'll sell Lasiga hardware, but the concept is fantastic because you can really move the pipe any which way, and Lasiga developed this a long time ago. And for an axial stop, I don't think there's anything better than this.
And if you support it on a piece of concrete or a rigid point, you will have zero movements on the pipe. You will always have zero movements on the pipe, no zero movements on the pipe if this is not connected to a piece of concrete or something rigid. If it's connected to the structure, you will have movements.
You'll have some movement. That's right. That's why you have to have raised steel. I mean, that's a structural guy's job to say, if I'm going to pull on this with whatever, these loads, incidentally, is a good point, and I'm not trying to negate that, but these loads here, these were not very large loads. They're very small loads, and so the movement can be zero even with reasonable steel. If it's huge loads, you definitely need to look at the flexibility of the steel, and that is one of the things that I had on an earlier slide. But this is to center the piping on the turbine, and even a small movement here, a small movement caused by a very low load would make an absolute nightmare of your turbine nozzles. But yeah, thanks for pointing that out. Okay, so I had to throw a picture in here because I love this picture. I found it on the internet. I'm like, this is so great. Man, if I had a crane and lawnmower, I'd be mowing my hedge like that. So my point is, some things are good enough to get the job done, but in support design, there's some choices that are not good enough, and they will not get the job done in certain locations, okay? Like I said, you're out there on a rack somewhere, it's all good. Alright, I'm going to show you some Roar 2, so you get a sense for the user interface. And to your point, I'm going to show you quickly how to import PCF files. I'm going to show you a video from my website, because for me to do it's going to take longer than for you to look at the video. So humor me on that. And then I'm going to show you in real time some basic handling of Roar 2, and then I'm going to talk about views, because I used to make kind of the inlet piping, the outlet piping. Now I put a lot of piping in one model, and because you can view just this or view just that, I'll show you that. I'll introduce you to that part, and then we'll talk about a couple more things. So,
in this video, I am going to show you how to import piping geometry into Roar 2 using piping component files, or PCFs. In Roar 2, click File Open, or simply click on the Open Project button. On the File Type pull-down, you will notice many neutral file formats that Roar 2 can read, such as Caesar2, Intergraph, Autoplant, but for this video, we will choose PCF. Roar 2 has the ability to open more than one PCF file concurrently. Typically, each pipeline name's geometry is stored in one PCF file. After choosing all the files wanted in the analysis, they are opened into a mechanically contiguous model. At this point, we are already in a position to run the analysis with the default load cases Roar 2 has created based on the temperature and pressure given in the import. We select all load cases and hit OK. Since we haven't saved the job yet, Roar 2 prompts us to do so. We will call this job test, and Roar 2 saves the job and runs the analysis. The job has run with no errors or warnings, so Roar 2 has saved, checked boundary conditions, designed the springs, since there were springs in this model, created and run the default load cases, dead load, operation, and shutdown. Shutdown is a so-called follow-up load case to operation, where loads associated with returning from operating to ambient temperature are calculated. Roar 2 creates the default reports for the spring design, support loads, stress analysis, and a plot of the geometry. Before we end the video, I'd like to point out that Roar 2 does retain the information that comes via the PCF file. The line numbers, which we arbitrarily called Pipe 1, Pipe 2, Pipe 3, and Pipe 4, are part of those piping segments data. Any support tags or nozzle labels are also retained. Thanks for watching.
alright, I can't do it that quick in real time, so humor me with my boring voice in the video. My wife points out, that's like the most uninteresting voice. And in real life, it's not quite as uninteresting. You might think, gosh, I kind of like that boring voice, man. I'm waking up to it.
And what about exporting to other programs?
Exporting. Can I answer it at the end? Can you remind me? I won't go there.
Got another question to this?
Yeah.
Are those sections imported or are they attached to an existing program?
I don't know if I understand.
If you have a program running or one system, you can attach another system to it and detach it.
In Roar 2?
Yeah, can you?
Yeah.
Or is it imported and stays there forever?
No. Like you can. I constantly bring more stuff in and put it all together. And to briefly answer your question, you can write PCFs, you can write CII files. There's some, you can get out of Roar 2 also. I mean, that would probably be the most useful. Alright. I'm going to show you in Roar 2 just some basic handling in real time. I think that'll be, even though these little buttons and stuff, doesn't matter. I'm going to tell you what I'm going to do, and I think you'll get the idea and the sense very well. So I'm going to go to my next model. The one that you just saw, I'm going to show you just a couple of highlights here. So one thing that I really love, and I'm not saying nobody else can do this, you just have to, I don't know what programs y'all use, but one thing I generally don't like is like iTunes that you manage my life somewhere. I'm old school, I like to make my subdirectories, I like to do it that. But one thing I love about Roar 2 is the revision manager. So if I go Alt, File, Save As, it ups the revision, one number I can put in here based on, in this case I'm on revision 5, and it pulls up 8. Because when I was in my hotel, I like saved it a couple times to 7, and so it knows the next revision number, and then I would type in there, based on revision 5, took out the loop, or whatever it is. And so now, I have jobs, one job I went over 100 load cases. Sorry, over 100 revisions, right? I mean, and I have a record of every revision and what I did and the models. Very handy to have. So I'll just save it here. And then, another thing is, after I import the PCF, there's two things that happen. One is, I generally end up with lots of little piping I don't care about and I don't want in my model, because it clutters my model. I generally want to erase it. Very easy to do. You can filter the model by line size, and then you just say, select everything, and delete, and it's all gone. Another thing, and I'm going to show you how to do that in a second. The other thing that I like is, it happens, probably never to you, but the model is not mechanically continuous. Okay? That is, the designer, a lot of times the designer sends me, can you check this? But they really haven't run the ISOs yet, they're not really ready, and in a gasket, you get a discontinuity mechanically. And if you don't notice that, your model is not, I mean, if you put a lot of work into it, at the end, if for example here, this wasn't connected, none of this matters to that nozzle, right? So those are two things I want to show you real quick. What I do, so to erase the small bore piping, I can see my mouse. There. I see it. All right. So I would go to this segment properties. Whoops, I clicked on the wrong thing. Where I can address and filter out segment properties. I go to this nominal diameter, is probably the easiest one. These are the pipe specs. Roar 2 is a pipe spec driven program. So in the pipe spec, you have your diameter, your insulation, anything that's physical about the pipe is in the pipe spec. So I usually start at the bottom and then work my way up. So I go, okay, I'm not going to delete that piping, I'm not going to delete that piping, not going to delete that. Those are the dummies with the springs, not going to delete that, not going to delete that. Okay, in this case, there's only one pipe spec I'm going to delete. So I've filtered it down to and I can select multiple pipe specs. Then I select it here, okay, and then I hit the delete button, and bam, they're gone. Now, you'll see in this case, there's small nodes here. Those are the nodes where the pipe was connected. This is very easy, either to erase by erasing with the eraser, erase the node, and going to this dot, which you can't see, or what you can do is highlight the piping or select all the piping for which you want to delete intermediate node. Remember, I'm doing this at the beginning after import, so I've not set any arbitrary nodes on. All the nodes that mean nothing, they're not a line number change, they're not a temperature change, they're nothing. They're just hanging out where something was connected or for no other good reason. A lot of times, you know, like guys that spool the piping, put a node in. I don't care about the spool, right? I don't want nodes all over my model, so I will select everything and delete all these nodes. I can do it with the eraser, or I can just say select all, and then I'm going to take the eraser and say delete all intermediate nodes. Now, if you want, like there's an intermediate node right there. These nodes are a little bit small. I can make those a little bit bigger. Everything's customizable, but I can make the nodes a little bit bigger. But all those intermediate nodes there, where the drain, vent, they're all gone now in one step. Right? I mean, it really, I can clean a model up that's important to your question very quickly, and I would never build anything by hand. If I can get any file, I don't care what it is, I want to get it. So the next point was this thing about discontinuity. So I'm going to show you, I'm going to create a discontinuity here, and I'm going to set a node. If you click closer to that side, the measurement will be from the node that you're closer to. You can, I don't like to read that window because you got to answer that question. So I'm just going to say, go 2 feet out, and then I'm going to put another node 1 foot out. And because of this graphics, I'm going to make these nodes a lot bigger. What is it? 7? Yeah, let's make them. Now you can see the dots. The dots are the nodes. All right. Let's erase this segment right here. Now I just take the eraser and it's gone. Again, it doesn't have to be mechanically contiguous. Word 2 doesn't really care. It can exist in space because there's absolute coordinates that it was imported in, right? And so now I could actually move this node a foot that way, and it would be on top of the other node and wouldn't necessarily be connected. Word 2 will tell you, hey, do you want to connect? Because you're right there. In fact, when you import a PCF, there's a parameter in Word 2 you can set that says any 2 nodes that are closer than a certain amount, merge them. I don't do that. I don't like something happening that I'm not completely controlled. I have that parameter set it. Don't do it. But I could move that node a foot over and it wouldn't be a discontinuity and you'd never see it because there's no gap, right? But the way I would detect it, even if it was moved over a foot, or let me just make it like that. The way I would detect it is I would go in here and I'd say, show me only end nodes, right? So I go to node names, I say I want to select the by geometry, and only end nodes. So the only nodes right now on the screen are end nodes. End node, check. It is an end node. There, end node, and what you'd see here, if you had a situation like a gasket, where it's essentially, you gotta zoom in forever and you're still not gonna see it, you'd just have an end node in the middle of a pipe, where the gasket would be, right? So, end node. So with one view you can get a sense and say, is there a mechanical discontinuity? In this case, it's obvious because there's a huge gap. How do you fix it? Well, there's a function where you can say, pick the 2 pieces of pipe and just connect them, even if they're not completely in line. Or you can go to the move command, and I'm going to move the one node to the other one. So I grab this little move, and I go to this node and move, and just click it to there. Word 2 says, should the segment be connected with node blah blah blah? And you say enter, yes, and then it's now connected, right? The node's still there. I can erase the node with erase node and click on. All right. I'm going to skip a couple things here, but I want to show you sloping pipe. I'm big on sloping pipe. Steam piping should be sloped. You might end up with it. Well, many turbines I've seen wrecked because some puddles, they have endless piping out here and there's dead legs. And so if you get slope piping with your PCF, that's fine. But I'm going to slope a piece here. So I'm going to select start to end node. Let's slope this piece. So I'm going to go from here to here, and I've selected this, and then I can do edit direction. Okay, and right now it's 0 in the X, something in the Y, and 0 in the Z. I'm going to say I want -1 foot in the Z. Okay, enter. Then Word 2 says move connecting segments. That means if they move this down a foot, you want all this globally in the global coordinate go down a foot? Yes, that will happen. If you say no, and I'm going to hit an N for no, you see what just happened? Right? So now it's sloped down a foot, but this piece is shorter. Okay. Now I can undo with Control. See how it popped up? I can redo with Control Y. Probably I don't ever redo. I always undo. So now redo. If you wanted to move this support on the slope pipe, I can move it, and I'll click on the node. And even though this node wasn't on before, Word 2 turns the 2 nodes on. It knows it's slope piping. And it will, and it will automatically say, put the axial check mark up here and say, do you want to go towards 168 or towards 110? I want to go towards 110, and I want to go like something obvious, 3 feet. You see? Now I just went down the slope piece of pipe. I don't have to go over and down. It knows, bam, and that's pretty convenient if you're in that situation.
What dimension did it take? The dimension of the slope pipe or the other dimension?
Yeah, that's a good question. The direction, in that case, if you pick axial, it's the direction along the slope pipe.
And normally we only have the direction of the horizontal pipe.
Well, then you have to, I understand the question.
dimensions. But now you have to go back and calculate how much.
Yeah, well, usually when you have slope, honestly, the difference isn't a whole lot.
Well,
It's better than going only in this direction and then having to figure out that. It's gonna be pretty damn close if you go straight. Yeah, but I understand your question. And, maybe there is functionality. I don't know everything about Roar 2. I mean, every job I learn. And so, if I say it doesn't work, honestly, after many years, I figured out something just in the fall that I'm like, how did this get past me for 30 years? Well, so, alright. So I'm gonna, if you wanted to, I'm gonna show you two more things. If you wanted to get rid of this loop because it's having a collision, I'm going to set a node here. Because if I erase this piece, then I got to add another piece. And so I'm going to just show you, I'm going to measure from here to there with the intention of copying this dy out. And then I'm going to use that number that's now in the edit paste buffer, put a node, and just put paste. And now I've just created a node with the same y coordinate. Now I'm going to erase segments. I'm going to erase this segment here. I'm going to erase that segment there. I'm going to select the window. This. I'm going to Control X. Take this as a handle. And I'm going to Control V. That is paste it here. Okay? And it asks if I want to retain the pipeline name. That is the line name. I say yes. It's the same pipeline anyway. And then it puts the elbow in automatically because that's part of the spec. And that's it. And now I have too high a nozzle load. I'll show you one example of an expansion joint if I can find it. There it is. Let's put a lateral expansion joint here and a foot out, and tons of manufacturers in here. But what we'll do is we'll just make it 3 feet long, 2 feet between the bellows, and make 2 rods vertical. It's more than 2 rods, so it just built me a lateral expansion joint that has all the right couplings of the rods being vertical. The reason, if you have more than 2 rods, the ends of that kind of expansion joint have to stay parallel. If you have 2 rods, then there's one plane in which the expansion joint can also act as an angular joint. And so, you can also copy and paste. If I would erase this valve, I'm not going to do it right now, but I erased it and took this valve and highlighted it and took kind of the elbow, if you will, and say copy this to there and put it in the existing pipe that's already there and insert the nodes. It would ask you, say, insert nodes into an existing pipe. Say yes, and yeah, and it would do it. All right, so I want to show you the GUI or the view thing, and then we'll move to back to the engineering. But let me show you the view. Because this is a really nice thing that I use very often with regard to the views.
Roar 2's graphical user interface is simple yet very powerful. Let me give you a quick tour of some highlights. In this video, I'll cover 2 general areas of the user interface: displaying what you want, how you want, and then saving views. Most everything in Roar 2's interface is customizable. The colors, line widths, text sizes, and styles, even what the mouse buttons do. As you can see, how things are displayed can be changed, but maybe more importantly, what is displayed is easy to control to a very detailed level. This button opens the window that controls what information is displayed. Let me highlight a few of the items on the list. It is helpful to know the location of the nodes, especially certain nodes such as at the equipment connections or support locations. Showing all the nodes in an overview of the model can result in overlapping of node names. Although the node names can be moved, it still may be desirable to not show all the node names in certain views. Here we select just nodes at boundary conditions. We can further specify which type of boundary condition, such as supports, and if that is not specific enough, we can select support types on a granular level. The boundary conditions themselves can be switched on or off here. Certain texts that are part of the model can be displayed, such as nozzle descriptions or support tags. This turns on a description of the spring, in this case, an anvil B268 size 7 type F. Remember, the size of the text or whether it has a box around it is all customizable. All these options give rise to a need to store various views for later recall. ROR2 can save views, which saves not only the zoom and orientation of the model, but also what was shown at the time of the save. Even views of results can be saved and later automatically inserted into the stress report. When models become larger, views of sections can be stored so that the proper amount of information is in each view. Complex piping systems where piping is overlapping can be presented in a much clearer way by using views where the hidden piping can be shown with a dotted line or not at all. Thanks for watching.
I used to really avoid making large models because it just gets a little unwieldy. But with these views, you can just say, here they are. And they're views of portions that are somehow palatable, right? I've made some way big models, and yeah. And with the views, it becomes something that can be handled. All right, so let's go back to, actually, I think I messed up something. Where's my, oh, okay, we'll go back to this, the tower. So now I'm going to show you how to couple it and have 0 loads. Think I can do it?
Yeah.
Is this something anybody's ever achieved?
Disconnect the nozzle.
What's that?
Disconnect the nozzle.
Disconnect the nozzle, okay. Don't laugh. That's a good idea.
That's a 0.
That is 0. Okay, we're going to do this. So I'm going to do it in 3 steps. I'm going to go into ROR2 and I'm going to show you this model. Okay, so here's the model. I'm going to pull up a view that I have saved, just like I just showed you views, and it's called the nozzle, because I wanted to make sure I can pull it up so I'm not fiddling around with it. Here's the nozzle, here's the support. The nozzle is node 10, the support is node 130. I'm going to pull up some results. I'm going to accelerate this a little bit without, I wanted to show you the coupled, the uncoupled, and then what I did. But I'm going to show you all of it at once. So, you're not going to be able to read this, but I'm going to tell you the important things. There are 3 dead load cases here. Okay, so here there's, and I called it coupled, which is essentially, I went to the nozzle, did it like anybody would do it. That's the coupled case. There's an uncoupled case. You get the prize. Not a free version of ROR2. And then there's a case called coupled with DB, because I was too lazy to spell deformation rate. That's how I'm going to solve the problem. So, here we go. I'll show you the results again. I'm going to walk you through this. So I put a hinge, which I can put the symbol on, but I'm not going to put it on right now. But at this node where I just double click, okay, they don't call it hinge anymore, they call it coupling. This is actually a beta version. It's coming out next week, but they now call it coupling. And so I put a hinge or a coupling where I decoupled everything, right? So it's all free. There's no QX, QY. You can say I want to couple some things, don't want to couple other things. So I freed it up. And the interesting thing is in ROR2 is I can activate and deactivate that coupling load case dependent, which is beautiful. Because now I have a load case called coupled, where it's coupled, and a load case called uncoupled, where it's uncoupled. All right. And I can look at it in this beautiful output. I'm going to read it. I'm only looking at the vertical load right now. So on the nozzle is 404 pounds coupled. And this is the deformation break that we're going to talk about momentarily. and on this nice support down here is 520 pounds. You gotta believe me or you gotta come up here. 404, 520. Client wants both of those down there. So now I uncouple it, and what's up here? 0. What's down here? 924. Beautiful. I sent him the analysis. No, because now the loads are up there too, and you're not gonna believe me. What am I doing? So I put, in order to, I'm not going to try to explain it completely, but there is like a point load function called deformation brake. And what it's doing is essentially saying, I'm going to cut the pipe, and I'm going to cock it a little, move it a little, whatever. And if you take the movements, which are 0.073 in the X, and even less than that in the Y and Z, and half of a tenth of a degree. I mean, these are little movements, but they're resulting in big numbers. These aren't big numbers because it's a small pipe, but they result in relatively big and uncomfortable numbers. Because my clients go to, I don't want these numbers. I mean, that's exactly the problem I don't want. So what do? I make this node, I've called it DB1 for no good reason, but it's deformation rate, and I have inserted the deformation rate, and now I've coupled it, and this third weight load case, dead load case, is called coupled with DB. It's just an arbitrary name, and you really don't need the first two. I leave them in just so I know what I did. When the piping geometry changes and I got to change the deformation brake, I want to go back to those low cases. But I can deactivate them. They're not good for anything. But here I'm showing them in the output, and in the coupled with deformation brake, I have 0, 0, 0, 3, -1, 0. Okay, almost perfect. There's such small movements. I didn't sit there and try to like put 10 decimal places of movement, right? So it's 0, and the client's happy, and it's coupled. And down here at node 130, it's 924 coupled. Okay, so the problem has been solved with the deformation brake. Not sure if your software can do it. I wouldn't know how to do it in another software, but ROR2 can do it.
I have a question.
Yeah.
Are you taking into account the flexibility of the nozzle? Is that the deformation?
No.
Where is the deformation coming from?
Sorry?
Where is the deformation coming from? Because that's the nozzle flange and the pipe flange are bolted together, right?
Yeah.
So when that pipe is gonna be hot or whatever, that load of the weight, it has to go somewhere.
It does. And in the operating case, when I can pull up the operating case, or I made this list specifically for this, but I can pull up, you will have a load on the nozzle. The nozzle's not uncoupled. It's completely as coupled as it was previously.
Yes, so how did you get the deformation? I mean,
it's not a deformation. I got it. All right, let me make sure I understand your question. The deformation that I used in the deformation brake was gotten by uncoupling, by taking it off and looking what's going on with the pipe. Just like a pipe fitter will go, what's going on? And then moves it. I mean, if you're going to call it a miter, it's kind of like, yeah, you got a kink in the pipe now. But the problem is, you can't have, let's forget this little twirling. If you have a straight pipe, you can't put a kink in the pipe because you're not going to end up with the nozzle, right? You have to end up with the nozzle. So you don't and so where's the kink? Well, that's the thing. The kink is not there. There is no kink. This is a way to put kind of like a point load, except a point deformation. It's a load entry in ROR2 that needs to be there for every load case.
I think it's just it's something similar to the Caesar, like a node in the C node. But the only difference is you can set a connection or not connection based on the different load cases. I think that's the major difference. And another thing I'm kind of curious about is, for this coupling, can you set exactly the degree of freedom, like
of course. I show you that.
That's a.
But it's different than the C node. The C node, it's like putting a deformation brake between the C node and specifying that.
Like a gap on the C node?
It's not a gap.
It's not a gap. It's
just a discontinuity. Go ahead.
It's just on and off.
During construction, when they put up the connection to the vessel, you're running up the pipe to the vessel, you're running up the flange to the vessel, and then they're just flipping the bolts, and there will be absolutely no movements.
That's why I have 0.
So there's no deformation on the nozzle. So if you put this in the program, then you're kind of tweaking it, which is not true.
No, you're not. Because I think and I think to your point too, I think the hold up right now is on the word deformation. Forget the word deformation. This discontinuity of deformation is literally what the pipe fitter would do.
But you don't know that, right? You're trying to...
I don't know it, that's why I ran an uncoupled case. So I would know that, just like the pipe fitter would know.
It's more like
And then
I have to manually take these 6 numbers and put them in as a deformation rate.
Well, you're assuming the pipe fitter is gonna do something to make it 0.
I'm assuming my client said, dude, I want 0 here and I don't want these moments and forces up there. Because my pipe fitter is gonna do that, but it's part of our plant's policy now that we've torn off nozzles, that you will put that pipe up there and you will not attach the bolts until, well, they probably attach the bolts, then put the jig in, then detach the bolts, then roll it up, right? And the jig is holding the pipe a little crooked, a little bit, but we're talking about it less than a 1/10 of a degree, guy.
Alright, do you have an ISO that'll show them exactly how you want them to set it up?
It's not important, because whatever the deformation rate is for them, and let's say it's hanging crooked, we're all very aware this pipe doesn't go in the way even the way this is done, it's not going in that way. Because when they put it in, it's not straight. Ours is perfectly straight, built in outer space with no gravity, okay? And then brought to Earth. And then gravity is brought onto the model. That's basically what we're doing, right? But in real life, you got a cherry picker, the thing's crooked from day one. And it's a topic that is very big and I'd love to talk about, because that's another discrepancy between, and another big topic. But so, no, because there's no way you're going to tell him to tweak it whatever, because his tweaking is going to be different, but it doesn't matter, because numerically, I need 0 load, and when he goes up there and the pipe's hanging crooked, he's going to make sure it's straight. What's important is, even if his is a little this way and mine's a little that way, I need 0 load, and I need to see how the operating case then, from there, acts, okay? And if he has it going a little bit, cocking a 1/10 of a degree that way, doesn't matter. I mean, the big picture is still the same, whether he's going this way or I'm going that way. There was one other question. We're gonna take questions at the end too. I think I'm almost done, and I don't want kind of people to feel like we're going down a hole, but go ahead.
How different is this from the cold spring?
This is not cold spring. Nothing to do with cold spring. It's not cold spring. I know I've lost everybody on the deformation rate, and I will spend time with you individually and go through exactly what's going on if that's of interest. Because this is pretty unique. But if you have a turbine, and Siemens is a pain in the neck about floating these pipes in and getting them straight. They are irritating. And I've been on the recipient end of not being able to get my pipes floated in, busting my tail, and not having enough restraints and ways to turn buckles and ways to tweak springs. And the guy's like, dude, call me when you're ready, you know? He's having a beer, he's getting paid, but he's waiting for me to get a pipe connected. And it's super painful, so I'm very, very sensitive about when I make piping designs, support concepts, and guides and so forth. This isn't cold spring. I don't like cold spring. I personally, don't hold it against me. I don't like cold design of springs either, but this is another topic for another day. It's a big topic.
Except, in my opinion, except the spring hand push, you can make adjustment. Otherwise, this coupling and coupling, you can, even though you assume that whatever the couple is not connected, you got a 0 node, assuming 0 on the nozzle. You still got a lot of nodes on that on brace. You cannot make any adjustment. So practically, I don't think it's any.
No, you're adjusting the pipe. The last weld is what you're adjusting. That's what you're adjusting. The fiddle. That's the only thing you're adjusting. Nobody's talking. The problem is you can't do a spring preload, and there's no spring. We don't even know the spring is in this thing, which is
unless you can make adjustment. Otherwise, it's coupling and coupling. I don't think it's.
All right. Well, I'm very happy to discuss this with anybody.
But it's a very great feature.
I just want to be.
It's a great feature, especially it's adjustable based on different nodes.
I'm not trying to not answer your questions, please. I love this stuff, man. I can be here all night. I want to respect your families and your time. That's all. Besides my dad. All right. and it is coupled, and it is no load cold. How that happens, I understand this is very mysterious for some of us, and please, take my card, I will get on a WebEx, and we will go through it in detail. There is no cold spring, the pipe's not crooked per se. You can't make it crooked, otherwise you never get to the nozzle, right? You need to get from here to there, and there's only one way. It's up this much and over that much, otherwise it won't be at the nozzle. Alright, let me speak briefly to the sources of divergence in dynamic calculations. Dynamic calculations, big subject. I'm not going to make a huge deal about it, but I do want to point out something again that's very unique in Roar 2. All the other programs, unless I'm really behind on their development, but I'm very certain of this, all the other programs do the non-linear calculus. I'm not trying to besmirch these programs. I love these guys. They've helped me a whole lot in my career. I'm talking to them more than they probably want to talk to me. But the dynamic analysis is based on what's called modal analysis or eigenfrequencies. You have this equation, mx double dot, cx dot. Everybody has nightmares from dynamics. But this is a linear ordinary differential equation. That means that these coefficients, m, the c, which is the damping coefficient, and the stiffness, are linear. They're numbers, right? So everything has to be linearized, so there's no gaps, there's no friction in your dynamic analysis. I'm sorry if you didn't know that. The gap is 0, the friction is 0. But the friction is kind of important because it does dampen the pipe. And as much as I've spoken badly about friction in your turbines, Siemens says, we want friction out on the pipe rack because we want it to dampen the piping system. We don't want everything hanging around and kind of blowing around. So, the problem is that at all the dynamic analyses, there's no gaps, no friction. And furthermore, there are, in the last couple of years, I've had a lot of nonlinear dampers. There's a company, GERB, G-E-R-B, that makes these buckets of goop, okay? And in a brutal way, but it's not very much more complicated. You have a stick that's on the pipe that's in the mud, right? Stick in mud in that goop, and this viscoelastic material has nonlinear properties that are frequency dependent. That is that this C is frequency dependent. It's very nonlinear. And if you want, in a linear calculation, you'd have to replace this by a spring. That's pretty much what you'd have to do. You'd have to replace it by a spring and say it resists movement. But it's a very nonlinear, frequency-dependent damping characteristic. I have one client that used, I'm not going to say it, but a good program, but they used ANSYS to do piping analysis. Think about this. I mean, I don't know if you've used ANSYS, but to do a piping system in ANSYS is a painful experience. It's not a piping program. It doesn't have, class 1, whatever. It was a nuclear job, and you got to start making up how you're going to put these stresses together. I mean, this is teaching ANSYS how to do pipe stress. It's a chore. But they needed to use ANSYS because they needed dynamic analysis with nonlinear boundary condition, right? So how you do that is you integrate this equation that's not as nice as this, but this is an equation you can solve analytically, which is essentially what you're doing with the eigenfrequencies. But when it gets crazy with the nonlinearities, you can't integrate it anymore. You have to integrate it numerically. Roar 2 has a module to do what everybody does here, and a module to do this, and it comes with Roar 2 to do the dynamic analysis with nonlinear boundary conditions. You can run two different dynamic analysis in the same model, and you can kind of see the difference. Again, I love this. I'm very practical. Lots of guys, oh, it's never going to work, and it works. I've been that guy. Well, this is terrible, it's like going to blow up, and then it works. And you're like, I'm not going to say that many times anymore. There's a lot of stuff that works that shouldn't work, okay? So we're not trying to make a mountain out of a molehill, but there's a lot of mountains that get created that I discover in the plant or in my auditing process where there's been failures. Okay, I'm just going to highlight a few more two features.
I still don't get how to do that.
We're going to talk about the definition.
I'll explain that.
I will explain it to you. Let me finish up. I got a couple bullet points and I'm done. Things I love about Roar 2. Material database. I hate going in there and typing in for every temperature some crap for material that's not in the database. I don't know what materials you got in your database. Road 2 has absolutely every single material from section 2 in the database. It's kind of crazy because some of the materials have the same name and a different footnote. They've organized them. I'm going to show you right now. I will show you whatever you want on a web meeting or after this.
I thought section 3 is for section 2 is for
Materials.
Oh, okay, yes.
Jacket pipe. If you ever have pipe in a pipe, there's elements in Roy 2 where you just say, here's the outer pipe, here's the inner pipe. It's a separate specification editor. Jacket pipe, you can couple it here, couple there. It's super easy to do. Stress codes. Roy 2 can do different stress codes in the same model. Obviously, in the FE portion of it that I talked about a little bit, in FE, this plates and shells model, you can't do a B31 analysis. You have to do a section 8, division 2, part 5. So you do different parts. And in addition, even in the beam theory model, and I run into this very often in the nuclear, where you have class 2 piping going to class 3 piping going to B31-1 piping. I just did a job with those 3 codes in the same model. So run part of the model class 2, part of the model class 3, part of the model B31-1. You get 3 stress reports. And the parts that aren't applicable, it doesn't run some weird stuff there. Alright. I love the integration features. The integration of the nozzle checking. That you don't take your loads and go over here. That all the load cases, no matter how many, all get checked integrally in Roy 2. There's also flange analysis. I don't do this. I don't know much about it. Please don't ask me. But it does like the bolt torque stuff and stuff. So all the load cases pass through the flange and figure out if the flange is going to leak and how much you got to torque it down. Again, I don't really use it. I like the integrated part. Fluid hammer load case, if you ever do that, you calculate the critical length and so forth, and then you apply the force vectors. In Roy 2, you tell it what is closing time, sonic velocity, and the flow rate. You click on the pipe you want, and all the force vectors go in at every elbow, proportional to the length, right? All right. So what else I got? I like the follow-up load case. The stratification load case is if the pipe has a different temperature at the top and the bottom, it makes a bow. I occasionally use that, and there's a load case that can do that, can make a different temperature at the top and the bottom. The FE, we talked about this. I use it mostly not to do a stress analysis because that is usually other people. I do it sometimes, but the FE, I love it because if I want a nozzle stiffness, quick nozzle stiffness, nobody's gonna give you nozzle stiffness. You go to WRC 297, British Standard 5500, whatever. It's not applicable in a lot of cases. You're too close to this. With literally, I can make one of these models with a couple clicks. Also, I did a job just recently where there was 2 nozzles too close, and if you read the footnotes in Appendix D, you can't apply the SIFs if the nozzles are too close. And so then you would have to make FE model. All that's integrated into the beam theory model and connected in. Fatigue analysis. Roy 2 has, you can say, I want to run this load case in and out, up and down, or whatever, 2,000 times in this one, this many times. Then with miner's rule, it has an SM curve in, and then with miner's rule, it will add it all up, because you have 50% usage from here and 20 from there, and then see if you're still under 100. That's all included. And then this is also something I've used a few times, thermal gradient. So Roy 2 will calculate the stresses if the inside of the pipe and the outside of the pipe have different temperatures. And there's a very, very handy formula in a class 1. Even if you're not in class 1 piping, I apply this to B31-1 or whatever. Where you have a linear distribution and a nonlinear distribution, and it adds it together. That's all built in. And the cycles, you say, we did this because there was a crack in a hot read line underneath the boiler in the boiler piping after 6 years. And I predicted that because they started that plant every day. And I predicted how many cycles of thermal gradient stresses it would take in Roy 2, and it cracked. This can also be added as part of the miner's rule to the other load cases, so that you can take the thermal gradient stresses and bring it in. So the dynamic, we talked about this. One thing I'll mention is we can accommodate different spectra in different buildings, okay? Not just at different elevations, and then we can do a bidirectional write to Caesar CII files, and then the last thing I'm going to talk to you about briefly is report generation. We have to document our analysis, and I do not like documenting and copying and pasting. It seems very painful. And I'm going to show you a short clip on that, and that's the last thing. So I had a question. Oh, yes.
A question on the temperature on the piping. Can you run the piping, for instance, on a cold flare where you have a negative on the bottom and especially on the ground flare, and you have to
You mean the range, right?
within the same section of pipe. The bottom of the pipe is negative, it's cryogenic, and the top of the pipe is hot because of the flare.
Yeah.
So this program will calculate you the boring of the pipe.
That's right.
And tell you the load.
And so both in this direction and in the thickness of the wall. Okay? Through wall. All right, let me show you one last little clip that I think you'll love, because if you like writing stress reports,
Creating stress reports in ROR 2 is a breeze. The report creation in ROR 2 is driven by a template. First, you have to select which template you want to use by clicking on Documentation and then on Select Report Template. You can choose a template that comes standard with ROR 2, or you can create your own. Next, you click on Create Report, and that's all there is to it. Let me explain to you the concept behind this very powerful tool, and then I'll show you how to create and edit the template in ROR 2. To understand the concept behind creating finished reports so seamlessly, I'm showing you a portion of a template and the corresponding report that is created when you click Create Report. There are two types of data in a stress report: data that does change from analysis to analysis, and data that does not change. Some examples of data that would typically not change is your logo and other text as circled here. Even this type of data is no problem to change at any time, in the template or in the final report. Multiple templates are also an option. In this first bullet point, the words at the beginning of the sentence will not change. But the code governing the analysis could change, and therefore it is represented by the link text. The report generator takes this information from the current analysis, in this case ASME B313, and inserts it into the report. The link can even be in the middle of a sentence. The next bullet point also has some descriptive text that would typically not change. This table is created by this link text. A plot or graphic can be inserted, as is the case with this link text resulting in this graphic. Well, you might be wondering how difficult it is to create links or what links are available. To answer those questions, let me open ROR 2 and show you how easy it is to create this very portion of the report from scratch. I'm going to display ROR 2 on only half the screen so we can see the template on the other half. Next, I'll click on Documentation and Edit Report Template. This opens two windows, the report template, and this window from which we'll pick our content and which will create the links we want. Let me populate the project and system fields in the header by inserting the proper links from ROR 2. This data is part of the model file when you save it. To check the text that is currently in the project field, we can click on it and choose Display. The project description is arbitrarily called XYZ Processing Plant. Similarly, the system is Feed Water Pumps to Preheater. By hitting the Copy button, a link is copied to the Edit Paste buffer. This link text is simply pasted into the template document where you want it to appear. We'll do the same for the system text. Now, we save the template and can have a look how our report is coming along by creating it here. The project and system links have now been populated in the header as well as on the title page here, where I had the same links. Let me jump to the page where we made the changes. We can close this report and continue to edit the template. This field gives the code to which the analysis was made. Again, we can check it by hitting Display. Let's copy it to the template. All the information you could possibly want in your report can be generated by links available here. So far, I've shown you simple text links, but there are lots of tables that are available for use in the report, such as a load case table, or which global loads were used in which load case. The table's fonts, column headers, column widths, and whether you even want to show that column are all customizable here, although the tables as listed here are very well thought out. From the Results section, I will insert the table under the Stress Analysis section called Max Stress Utilization, Summary of All Equations. Then, from the Graphics section, I'll copy the link for the saved view, highest expansion stresses. The video entitled Graphical User Interface introduces you to how views are created and saved. Even though there are templates provided with Lord 2, I hope you've been able to see that creating your own template is easy and intuitive. Afterwards, generating a custom report is just one click away. Thanks for watching.
Well, since I sell engineering for a living, I look for ways to save time, because saving time saves money, makes it cheaper. Importing, big time saver for me. Making these documents, for me, it's a big time saver, and I don't like doodling. The whole thing comes out again. With whatever output file, everything, appendix, this is actually an older version of Word 2. I made that video with, it's gotten better than that. And if I had a company that had 10 or 20 guys, I would really like the template, because you can change it and you'll all agree how it's going to look, and then bam, they're all going to look the same. And I think that's, let me make one more slide. I just wanted to show you, in case you're wondering, I took off the long list of users. These are some companies that use Word 2. Alright. Go ahead. Did you have a question?
Can you print or export piping isometrics out of the program?
Sorry, say that again?
Can you print or export the piping isometric?
I usually make these views, and then I print them, and they end up in the report.
It's a regular piping isometric.
The regular piping, yeah, there is an isometric generator. I'll be frank with you, I don't think it's that great. I don't use it. But yeah, there is. It's all Word 2 ISO. But honestly, it's kind of like, I like making my views and putting those in the stress report.
No, it's when my personal experience is the way I use it. I'm running piping isometrics and send it to the client, and very well received, and everything required is on these isometrics. Just making a view, it just doesn't cut.
No, but everything's on those views that I made. Yeah. Everything that I want, that I need, like the node numbers, the functions, that's all on those views. The piping isometrics today, the reason I don't make it into, like, I don't use it, is because generally, the isometrics are made by Isogen, they're coming from the designer, they have a set of isometrics, they don't need another set of isometrics from me. That's why I kind of got away from the whole need to, so I make what I call stress ISOs from this program, and you can look at that some more, but
No, it's not.
But yeah, and please, anybody that has, I can still be here as long as you want. I can answer questions. I want to respect the people that kind of took this time, and we got off to a very late start. But thanks for hanging in there with me, and thanks for having me. And hopefully I get any questions today.
I think, like, just to close the event, I would like to say thank you so much to Georg. It was such a good presentation. I was looking at people because I was like at the very end of the room, and I saw the people, everybody was very interested in your presentation. Again, like, you're a very good speaker, just to begin with, but then also because for some reason, since I started doing stress engineering, I really use the same software, you know? So it's also good to know that there are some other options. It's good to know that there are some other minds behind this activity that we do, which is piping stress analysis. And then just to see the way that every different company, every different engineer approach the same problem that we have. You know, like, it's so important, like what you said about the dynamic analysis, where we cannot make a non-linear calculation, and now we have that option. So there are like benefits, like things that you like, things that you don't like. It's obviously a challenge to start learning a new software. But I mean, the good thing is that we have several options with all the different software that we have around the world. So I think it was a very interesting presentation. It was good to learn about you, to learn about your experience. I was so glad that we came to Houston. we're like good friends now. We're like, sometimes it's really difficult to convince people to like come to Houston for an event, like hey, we're gonna have some good amount of people, and they think that oh yeah, I don't know, it's like such a risk. Even honestly, really big companies that I'm trying to support, they do not want to come. So right now, Georg came to the ESI and then he wanted to come. Like I'm really happy, I'm really excited. So it's just like, Georg, so nice to have you here. Like he has a lot of experience. If you need any kind of help with your stress calculations, not just stress analysis, but at the same time to do some evaluations or QAQC, I would put it that way, like QAQC, in case you have analysis from, not only from other countries, but also in your same company, you have a need to have QAQC. I think it's a really good option. The experience.
And I do that in Caesar many times. People send me the Caesar stuff, and I kind of do the QA stuff. I don't try to sell more than two. I make my money with engineering, but I just have to show you some of the other tools out there. And yeah, thanks for.
Yeah, no, like thank you so much, Georg. It was so nice to meet you here tonight. Thank you guys. I hope to see you very soon.